Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the vector algebra. So first, we will understand that what is scalar and the vector, and then we will learn about the vector addition and the subtraction. And then after, we will also learn about the scalar field and the vector fields. So in the introductory video of the electromagnetics, we have seen that this electromagnetic theory can be better understood with the help of the Maxwell equations. And to understand these Maxwell equations, we should know the vector algebra and the vector analysis. And for that, first let us understand the concept of the scalar and the vector. So the scalar quantities can be expressed just using their magnitude. For example, this temperature, time, population, mass and the electric potential are the example of the scalar quantity, because these quantities can be expressed just using the magnitude. For example, if we want to represent the temperature of some city, then we can say that the temperature of the city is equal to 35 degrees Celsius. Or if we want to represent the mass of some object, then we can say that is equal to 60 kg. And likewise, if we want to represent the electric potential or the voltage between the two nodes in the circuit, then we can say that voltage is equal to 13 volt. That means the scalar quantities can be represented just using their magnitude. On the other hand, if we see any vector, then it has both magnitude as well as the direction. So this velocity, force and the acceleration as well as the displacement are the example of the vectors, because these quantities have both magnitude as well as the direction. For example, if you want to represent the displacement, then it is important to mention the amount of the displacement as well as the direction in which this displacement is made. Similarly, from the electromagnetic perspective, this electric field intensity is the example of the vector. So since the vectors have both magnitude as well as the direction, so typically they are represented by the arrow on top of the symbol. So for example, the velocity is represented by the symbol v with the arrow on top of it. Likewise, the force F and the electric field intensity E can be represented like this. Now in the three-dimensional space, if we have some vector A, then this is how it can be represented. And mathematically, this A can be represented as this AX times AX plus AY times AY plus AZ times AZ, where this AX, AY and the AZ are the components of this vector A in the direction of X, Y and the Z. And if we see the small AX, AY and the AZ, then they are the unit vectors in the direction of X, Y and the Z. That means if we see the vector AX, then it is a vector of magnitude 1 in the X direction. Similarly, these AY and the AZ are also vectors of the magnitude 1 in the Y and Z direction. That means if we see the magnitude of all these vectors, then that is equal to 1. And that is why they are called the unit vectors. So when this unit vector AX is multiplied by the component AX, then the magnitude of the unit vector will also get multiplied by the same amount. So it shows that this vector A has the component AX in the X direction. Likewise, this AY times AY represents that this vector A has the component AY in the Y direction. And likewise, we can say that the vector A has the component AZ in the Z direction. And when we add all these vector components together, then we will get this vector A. So basically, when we add all these vectors together, then it will lead us to the some point P in the 3D space. And from the origin, when we draw a vector towards this point P, then we will get this our vector A. So whenever we are representing this vector A mathematically or in the 3D space, then its X, Y and the Z components are already representing its direction. But now let us see how to find its magnitude. So the magnitude of this vector A can be given as the square root of this AX square plus AY square plus AZ square. And that is how we can find the magnitude of this vector A. So now we know that this AX, AY and the AZ represent the unit vectors in the direction of x, y and the z respectively. So similarly, let us see how to find the unit vector in the direction of the A, and let's call it as the AA. So this unit vector in the direction of the A can be represented as this vector A divided by the magnitude of this vector A. So as you can see, if we try to find the magnitude of this unit vector, then it will come out as 1, because that will be equal to A divided by A, and that is equal to 1. That means this expression represents the unit vector in the direction of the A. So for example, let's say we have some vector A that is equal to 3ax minus 5ay plus 4az. So its magnitude can be given as the square root of this 3 square plus minus 5 whole square plus 4 square. So that is basically equal to square root of ax square plus ay square plus az square. And in this case, that is equal to square root of 9 plus 25 plus 16. That is equal to square root of 50. So now, if we see the unit vector in the direction of the A, then that is equal to this vector A divided by the magnitude of the vector A. So that is equal to 3ax minus 5ay plus 4az divided by the square root of 50. And if we further simplify it, then this unit vector A is equal to 0.424 times ax minus 0.707 times ay plus 0.565 times az. So in this way, we can find the unit vector in the direction of the given vector. And of course, its magnitude will be equal to 1. So now, let us see the vector algebra. And let us see the vector addition and the vector subtraction. So first, let us start with the vector addition. So this vector addition is similar to the normal algebraic addition in the many aspects. So let's say we have two vectors a and b in the Cartesian form. So now when we do the addition of these two vectors, then it will be done component wise. That means during the addition, the x, y and the z components of each vector will be added. So in this case, if we do the addition, then this a plus b will be equal to 7ax minus 2ay plus 6az. And let's say this a plus b is equal to c. So similarly, this vector addition can also be done graphically. And to understand that, let us take two simple vectors which has components only in the one direction. So let's say this a is equal to 3ax and the b is equal to 4ay. So in the Cartesian coordinates, this vector a and the b can be represented like this. That means here, this is the vector a, while this is the vector b. So now, while performing the addition of these two vectors, what we will do? We will place the tail of the second vector to the head of the first vector. And of course, we will keep its direction as it is. That means now during our addition, this is our vector a and this is our vector b. And now, the resultant vector is drawn from the tail of the first vector towards the head of the first vector. And that is how we will get our a plus b. So this graphical method of the addition of the two vectors is known as the head to tail method. So if you want to see the same thing in the 2D space, then you can check the given link in the description. So here, you can give the x and y components of the two vectors. And once you provide that, then it will give you both addition and the subtraction of these two vectors using the same method. So similar to the head to tail method, the same addition can also be done graphically using the parallelogram method. So to understand that, once again let us take the same vectors. So first, let us draw both vectors from the origin. That means here, this is the vector a, while this is the vector b. So here, now we will complete the parallelogram by drawing the remaining lines. So here, this line is parallel to the vector a and it is of the same length as the vector a. Similarly, this line is parallel to the vector b and also it is of the same length as the vector b. So here, since both vector a and the b are originating from the same origin point, so this vector a and the b are the two adjacent sides of the parallelogram. And now, the diagonal of this parallelogram that is drawn from the same origin represents the addition of these two vectors. That means here this vector represents the a plus b. So this is the another graphical method for the vector addition. So now similar to the vector addition, let us see the vector subtraction. So let's say this is the vector a while this is the vector b. So mathematically here this vector subtraction is similar to the vector addition. That means here the subtraction of the two vectors is performed component wise. That means here during this a minus b, the x, y and the z components of both vectors are subtracted from each other. So for the given two vectors, if this a minus b is carried out, then it will come out as minus 2ax plus 2ay plus 3az. And let's call this resultant vector as the vector c. So as you can see, this vector subtraction is very similar to the vector addition. So similar to the vector addition, this subtraction can also be carried out graphically. So once again, to understand that, let us take the vector a and b which has only one component. Let's say this a is equal to 3ax while the b is equal to 4ay. So first of all, let us represent these vectors graphically. So here this vector will be the vector a while this vector will be the vector b. Because as you can see, this vector a has the component only in the x direction while the vector b has the component only in the y direction. Now here, since we are performing the a minus b, so we also need the minus b vector. Because this a minus b is similar to the a plus minus b. So here, we can get this minus b vector by reversing the direction of this b vector. So now, this will be the minus b vector. And now, to get this a plus minus b, we will follow the same procedure that we have followed earlier. That means here, we will align the tail of this minus b vector to the head of the a vector. And now, the resultant vector is drawn from the tail of the vector a towards the head of the vector minus b. And this vector represents a minus b. So the method which we have used over here is same as the head to tail method. And here, the same resultant vector a minus b can also be found using the parallelogram method. So let me also show you that. So once again, we will take the same example. So first, let us represent this vector a and the b in the 3D space. So once again, here both vectors a and the b are starting from the same origin. But here, since we are performing the subtraction, so instead of the vector b, we will require the vector minus b. So for that, just let us reverse the direction of this vector b. So here, this minus b vector has the same magnitude as the vector b, but its direction is opposite. So here, this vector a and the vector minus b are the two sides of the parallelogram. So now, let us complete this parallelogram by drawing the remaining two sides. So this side is parallel to the vector a and it is of the same length. And likewise, this line is parallel to the vector minus b. And now, the diagonal of this parallelogram that is drawn from the same origin represents the addition of the vector a and the minus b. Or in other word, it represents the a minus b. So that is how the addition or the subtraction of the two vectors can be done graphically. So if you want to practice more and see that graphically, then you can visit the given link in the description and check the addition and the subtraction of the 2D vectors. And if you want to see the same thing for the 3D vectors or the vector which has the three components, then for that also, the link is provided in the description. So please check those links so that you can have a better idea about the vectors. So these vectors also follow some basic laws of the algebra. So let's say we have a three vectors, that is a, b and the c. So for these three vectors, these are the commutative law, associative law and the distributive law. So as you can see, the basic laws of the algebra are also followed by these vectors. But similar to the algebra, among these laws, the commutative and the associative laws are applicable only to the vector addition. But as you know, the vector subtraction does not follow these two laws. So in this way, the addition and the subtraction is performed on the vectors. So all the vectors that we have seen so far are the position vectors, because all these vectors are originating from some reference point O and they are directed towards some point P in the 3D space. So basically, they are representing the position of some point P in the 3D space, and that is why they are called the position vectors. So let's say the reference point or the origin is equal to O, and let's say some point P in the Cartesian coordinate is equal to 4, 5, 7. So this position vector that is directed from the origin O to the P, or this RP, can be given as 4ax plus 5ay plus 7az. So that is how all the vectors that we have seen so far are represented. Now similar to the position vector, we also have this displacement vector, which is sometimes also known as the distance vector. So this distance vector shows the displacement from one point to the another point. So in the Cartesian coordinate system, let's say the one point is equal to point P while the another point is equal to Q. So this displacement vector RPQ shows the displacement from the point P to the point Q. So now let us see how to represent it. So for some point P, its position vector will be RP, right? And similarly for the point Q, its position vector will be equal to RQ. And we know that as per the vector addition rules, this RP plus RPQ is equal to RQ. Or from this we can say that this RPQ is equal to RQ minus RP. So let's say the RP is equal to 4ax plus 5ay plus 7az, and the RQ is equal to 7ax plus 8ay plus 10az. That means here this point P is 4, 5, 7, while this point Q is 7, 8, 10. So here for the given 2 points, this displacement vector RPQ is equal to RQ minus RP, and that is equal to this 7 minus 4, that is 3ax plus 3ay plus 3az. So that is how we can find this displacement vector, and in this way we can represent any vector in the 3D space that is not originating from the origin. So far we understood what is scalar and the vector. So similarly, now let us understand the concept of the scalar field and the vector field, because during our discussion of the electromagnetic theory, we will come across many vector fields. And to understand that, first let us start with the scalar field. So if we see the scalar field, then it is the collection of the scalars. So in the scalar field, each point in the space has the magnitude, and mathematically it can be represented as the function of x, y and the z. So as we move around the space, then the value of the function or the magnitude of the function will change, and the value at the specific location will depend on the expression of the given function. So the simple example of the scalar field is the temperature in the room. So as we move from the one point to the another point in the room, then the value of the temperature will change. Of course, this change will be very subtle, but there will be a definitely change in the temperature as we move from the one point to the another point. Similarly, the pressure in the atmosphere is also another example of the scalar field. And from the electromagnetic perspective, the electric potential or the charge density are also example of the scalar field. So in electromagnetics, apart from the scalar field, we will also come across the vector fields. So in the scalar field, we have seen that each point in the space has the magnitude. So similarly in the vector field, each point in the space has its own vector. That means each point in the space has magnitude as well as the direction. So in case of the vector, we have seen that it has a component ax, ay and the az in the respective direction. And for the given vector, they are the constant. On the other hand, in the vector field, the component ax, ay and the az are function of the x, y and the z. So as we move around the space, then the value of this component ax, ay and az will change, and accordingly the vector at the specific location will also change. So let us take one simple example, and through that let us understand the concept of the vector field. So let's say we want to find the vectors at the following location. So first let us find the vector at this position, and let's call it as HA. So here, to find this vector A, we will put these values of the x, y and the z. So if we put these values, then this HA will come out as this 2 times 1 times 3 times AX minus 1 plus 5 times AY plus 5 square times AZ, and that is equal to 6AX minus 6AY plus 25 AZ. So this will be the vector at the position 1, 3 and the 5. Similarly, let's find another vector at this position, and let's call it as the vector HB. So here, to find this vector, we will put the value of the x, y and z as 4, 1 and 6 respectively. That means here, the first component will be equal to 2 times this 4 times 1, and similarly, the second component will be equal to 4 plus 6. And likewise, the third component will be equal to 6 square. That means this vector HB is equal to 8AX minus 10AY plus 36AZ. So in this way, as we move around the space, then we will get the different vectors at the different location. So in electromagnetics, the electric field intensity and magnetic field intensity are some of the examples of the vector field. So later on, we will see them in the detail. But I hope in this video, you understood what is scalar and the vector and how we can perform the vector addition and the subtraction. So in the next video, we will learn about the vector multiplication, and we will see the two types of vector multiplication. That is the dot product and the cross product of the vectors. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.